Welcome, everybody. It's great to have you here at GDG Dallas, and I'm excited to introduce Lauren Yu, who will be presenting Understanding iOS from an Android Perspective, a busy developer's guide to native iOS apps. Lauren Yu, it says here, is the senior Android software engineer at the New York Times, but I believe I saw she got promoted recently. You'll have to tell us a little bit about that, Lauren. Developing Android and iOS libraries from the app for the app platforms team at the New York Times. When she's not writing code, she's usually training her 3 dogs. You can find more information on her past talks and work, and maybe even about her dogs, at laurenyu.github.io. Take it away, Lauren.
Welcome, and thank you all for giving me the opportunity to speak with you today. And welcome to Understanding iOS from Android Perspective. As Luke mentioned, I'm Lauren Yu, and I am now a staff Android engineer at the New York Times, and I work on what I call our app platforms team, where I develop and integrate our Android and iOS core feature libraries into our mobile apps. So today we're going to take a look at developing for iOS from an Android perspective. Now, this presentation is actually meant to be very interactive. So if at any time you have a question, feel free to unmute and just go ahead and ask it. Or there's different topic sessions, but at the end of each topic session, I will be stopping and pausing for asking for any questions. Unfortunately, with this kind of setup, I can't exactly see all the chat stuff. So I will try to check the chat at the very end. Okay. So before we get started, let's start with the caveat. For simplicity's sake, I will be focusing on Swift versus Kotlin, as well as the latest iterations of iOS development and Xcode. And for this presentation, we're going to be comparing the Android and iOS platforms. For the comparison, iOS will always be on the left and Android will be on the right. And for many of these code and app examples, I'm going to be using my Pet Adopt sample app, which was built with Petfinder's free database backend that searches through thousands of animal welfare organizations to find adoptable animals for given queries. Now, I built this Pet Adopt sample app to have both Android and iOS versions, with each feature mirrored per platform. And these are the topics we're going to discuss today. First topic is the design differences between the Android and iOS platforms. So iOS platforms and apps are designed based off of the Apple Human Interface Guidelines, whereas in Android, we use material design. So one of the main differences between the platform's designs is the phone controls. So with iOS phones, we actually only have a home button available. So on the newer phones, this is triggered by swiping up from the bottom of the phone. And on older iPhones, you actually see a dedicated hardware button. Unlike with Android, where we always have some kind of home button and back button, especially when we're dealing within the app. So what this means is when you're dealing with an iOS app, the only way to exit the app is to use the home button. And a back button, when it appears, is only for actually navigating within the app. So essentially, when you're developing for iOS, there is actually no back pressed, like back button specific callback. And actually, they have a view will disappear or on disappear that will be called whether you're navigating forward, backward, or exiting the app. So it's just important to note that you shouldn't expect this on back press specific callback that we would have with Android, because we always have a back button present. Now, another difference between Android and iOS is with the app's design in terms of control. So for example, iOS does not have radio buttons like Android does to select a single option from a group of options. Instead, an iOS developer can create a segmented control in case they want to have only a few options. They can also create a picker, which will allow them to have multiple options to create a spinner to choose an option. Or an iOS developer can code their own list to show a check mark on one option out of a group of options. Now, likewise, an iOS developer does not have the checkboxes that we have in Android to select multiple options out of a group of options. Instead, an iOS developer can choose to change that list to show check marks on multiple options, or actually the iOS Human Interface Guidelines suggest creating a switch per option to toggle on or off each option. And then finally, when you're dealing with design and the design differences between Android and iOS, one of the main differences is how errors are handled. So in iOS, according to the Apple Human Interface Guidelines, all errors are handled by alert error dialogue that will pop up and allow the user to know about the errors. iOS developers can also choose to create these error label texts that are very similar to our inline errors. But according to the application interface guidelines, all errors should just be handled by error dialogs. This is very different from Android, where in material design, we should really avoid these error dialogs unless it's a major blocking error. And instead, we generally try to use inline errors or some kind of snack bar. Moving on, let's talk about Swift versus Kotlin. So let's start simple with declaring variables. Constant variables are declared with let in Swift, equivalent to val in Kotlin. And mutable variables are declared with var in both languages. Now, focusing on optionals, we can use the question mark syntax on the type to declare either variable in both languages as optional or nullable. And note that we use nil for null in Swift. Now, say we wanted to get the optional's value or run a function on it, we can use the question mark dot syntax in either language. So in Swift, this is called optional chaining, and it's equivalent to the safe call in Kotlin, where we'll only get that variable or call that function if, for example, person is not null. Now, say we wanted to actually get the variable's value and provide a default value if that value or person is null, then we can use the double question marks in Swift. This is known as nil coalescing, which is the equivalent to the else operator in Kotlin. But the main difference between optionals with Swift versus optionals with Kotlin is how in Swift, if you check if a person is not null or a variable is not null, we don't get that automatic implication of the person not being not null in the future of that if check. Unlike with Kotlin, where we have the implied nullability or not nullability after an if check. The same applies with type casting and type referencing. So for example, even though I've checked that human is a person in Swift, if I try to use human as a person, I must force unwrap it in Swift, unlike with Kotlin, where this is inferred for us. Likewise, even if I force unwrap person, for example, to be not null, I must force unwrap it every time in Swift, unlike with Kotlin, where a single force unwrap is sufficient, and from then on, that variable is treated as not null. So how do Swift developers or iOS developers handle this sort of optionals and non-optional nullability? Well, we have guard-let and if-let to change the variable to a new state, or even use the same variable name to change the current variable or create a new variable. The main difference between guard-let and if-let is that guard-let will usually return or throw an error in its else case. This follows the pattern of early exit, where we have assumptions at the top of a function, in which if we pass those assumptions, we can then continue on in the function and have our variable set to our new state, and otherwise we will early exit out of that function. So as you'll notice that once we've passed the guard-let, our person variable is then set to its new state. Unlike with the if-let, the variable is only set to its new state within the scope of the if-let. So this is more helpful in the case of if human is a person, then I can do something with that. Otherwise, I can do something else and then continue on the function. Now let's take a look at functions themselves. Swift declares functions with the fuck keyword, which is equivalent to the fun keyword in Kotlin. Now let's take a look at returns from functions. So in Swift, you can have an unlimited number of return values. It is suggested for a large number of values that you return a struct or a class instead. This is very different from Kotlin, where we can actually only return a maximum of 3 values with either a pair or a tuple. And if we want to return a larger number of values from a function, we must create a new class. Now let's take a look at a difference between parameters with Swift and Kotlin. So as you see here, we have a create person in Swift, and there's a new underscore in front of first name. This allows me to, when I call create person, to not have to provide the parameter name. So in Swift, parameter names, when you call the function, are required to be typed in unless you have the underscore in the function's declaration. This is very different from Kotlin, in which the parameter name can be provided, but it's actually implied based off of the ordering of that parameter in the function. Now let's take a look at some things we've been using behind the scenes: protocols, structs, and classes. So protocols are essentially the equivalent to Kotlin interfaces, with one exception, and that is that protocols cannot provide a default implementation. So as a workaround, Swift developers can extend their protocols to provide this default implementation. We'll talk about extensions more in a moment. Now let's focus on structs and classes. So both structs and classes can provide stored variables or functions. But the main difference between structs and classes is that structs are value types, meaning when you're passing them around, you're actually passing a copy of their value. Now, Kotlin does not have an equivalent to structs, but this would sort of be like having a data class that you ran a dot copy on every time you passed it around. So for example, here we have a person struct and we reassign it to person 2. This is actually passing a copy of the person struct. So when we change the name value of person 2, we don't essentially change person 1. Unlike when we have a dog class and we reassign it to dog 2, once we change dog 2, we're changing the reference to the original dog. Thus, we change the original dog. Another difference between structs and classes in Swift is that classes can inherit from other classes or be inherited from, whereas structs cannot inherit or be inherited from. Now, both structs and classes can implement protocols, but only classes can do inheritance. Now let's focus back on classes and compare Swift versus Kotlin. So with classes in Swift, all classes are default open within the same module. So this is very different. So in Kotlin, where all classes are default closed or final. So for example, in Swift, the only way to make a class not inheritable is to mark it as final. Whereas in Kotlin, everything's default final. So the only way to inherit from a class is to mark it as open. However, if you're going to a different module, so say I wanted to inherit from dog class, and dog class is in a library module, is different from my at module, I must mark dog class as open. And this follows the same paradigm as Kotlin. Now, as promised, let's talk about Swift extensions. So all protocols, structs, and classes are extendable. And in each extension, you can add more functionality, different implementations, more implementations of protocols, or just more functions themselves. However, you cannot add more stored variables. So oftentimes when you're dealing with Swift code, you'll often see in a single file extensions of your same class split out by extension by function or feature functionality like you can see here. But these functions, these extensions can also be done in other files very similar to Kotlin extensions. So if you want to see where your class was extended or overridden, it's best to search a class name to find where it's been extended. Okay, any questions so far?
I have one. From the perspective of someone who doesn't code a lot anymore, I would say that Swift and Kotlin look very, very similar. Do you think that makes it easier to go between them, or is it almost harder because there are such subtle things? I guess it's kind of a question not only about the language, but also about the IDEs, like those subtle differences. Do the IDEs tend to find all of those, or do you end up having issues because they kind of look similar, but you might forget some of that default behavior?
I would say that for the languages, the similarity makes things very easy because for the most part, unless it's like a small syntax difference, unless it's those things that I've pointed out here, you can generally use the same rules for each language across languages. So except for these gotchas that I've pointed out, in general, it's just like the difference between a question mark dot, and then you just realize, oh, I used the wrong syntax. What's really going to be different in development, I think, is with dealing with the IDEs, because the way, we're going to go into this in a moment, the way Android Studio and Android is built and run is very different from how Xcode works. And we're going to go to that actually in the next section. That's a great question. Thank you. Any other questions? Did I answer your question?
Yeah.
Okay, great. Okay, I'm going to move on. So next topic is app setup and structure. So let's go through some Xcode basics that are associated to app setup. So when you're opening up an iOS app, you're either going to open up your project or your workspace. Note, if you have a workspace available, you should be using the workspace to open up in Xcode, so that make sure that all of your projects are opened up properly. Now, at a high level, a workspace is basically a document that tells you what projects it contains as well as some other documents. And you can think of a project as representing an app, library, or a framework. And it has things like what source documents that app, library, or framework needs, what is the file structure, or what are some basic project-wide settings. So think of this like Android's root build.gradle. And each project has within it one or more targets. And a target tells Xcode how to build or run each app or library. So you can think of this like the app's build.gradle. So when you open up your workspace, you'll see your projects listed out. If you click on a project, you'll actually be taken to the project settings within Xcode, which also includes which targets there are for that particular project. Should you click on the target, you will be taken to your target configuration, which has important information like your unique bundle identifier, which is the equivalent to the Android's application ID. There's also what frameworks or libraries that your target is depending on. And finally, what's interesting is they have your build phases, which has your compile sources for that target. And if you've developed with Swift, this is what you're setting when you're setting a target membership on each file. Okay, moving on, let's talk about the iOS app structure. So first off, some terminology. When I'm talking about a bundle, I'm talking about the executable app or framework. A framework is essentially like an Android library module. And coming back to how to build and run an iOS app, you're going to be working with your application bundle, which consists of what we call an info plist, which is basically how we can build and run our app. This is our configuration file, the executable, as well as some resource files. So let's take a closer look at the info plist. If you were to open up in Xcode, it would look like a table like this. Its full name is information property list. It's very similar in configuration of parts of the Android manifest as well as build.gradle. Essentially, though, it's actually an XML file that's encoded in UTF-8. So if you were to look at the source version of this table, it would look like this. Now, if you've worked with info plist, you might notice that some of the keys and strings look awfully similar to some things you've seen before. And that's because you have in your project settings or your target configurations. So every time you change that in Xcode, it's automatically going to either update your info plist or update what we call the PBX proj file, which is part of your project-wide settings. Okay, let's talk about working with dependencies. So a lot of iOS developers use Cocoapods, which is a third-party scripting system to handle dependencies because it's very difficult to do so with iOS and Xcode. Some iOS developers also choose to use SPM or Swift Package Manager, but for today, we're just going to focus on Cocoapods. Now, as I mentioned, Cocoapods is a third-party scripting system. Basically, what you do is you have what they call a pod file in which you specify your dependencies, you run a script, and then Cocoapods will download all of your dependencies and hook them up into Xcode for you. So let's take a look at pod files in Cocoapods and compare it with a build.gradle file with dependencies for Android. So in a pod file, to specify your dependencies, you have to specify the target you want those dependencies for. This is because Cocoapods is actually outside of your project. And so it needs to know what particular target you want that dependency for. Unlike with build.gradle with the dependencies, it knows generally where those dependencies are supposed to go based off of its location in the file structure. Now, in a pod file, we specify our dependency with pod as a keyword, and then we give the pod the dependency's name as well as the dependency's version that we want. This is very similar to in build.gradle, where we specify an implementation with a package name and then the package version that we would like. So how can we just get a dependency just by its name? Why don't we have to provide something like Maven or Google, some repository we can get it from? Well, this is because Cocoapods actually has an internal central repository, which it calls trunk, that contains all these dependencies and libraries, which are known as pod specs within it, that it provides to all of its scripts. This makes it really easy for iOS developers to publish new libraries and to search for them based off the library name. It's also allowed for developers to provide their own URL and specify their own pod specs, which makes it really easy to have internal libraries and pod specs to specify like a GitHub URL from your internal app. So how does this all work? Once you specified your pod file of your dependencies that you'd like, you run your script, which in this case is pod install. What this does is Cocoapods downloads your dependencies from the URL or the internal trunk and creates a new pod project framework project into your Xcode. It then hooks into the targets you specified to reference those frameworks that you've created as a dependency. So what are some popular dependency libraries for iOS developers? If you want to do HTTP calls, there's Alamofar or AF networking. This is very similar to Retrofit. If you'd like to do image rendering or animation rendering, there's a library called Lottie. And for those developers who really like ArcJava, there's also ArcSwift, or you can just use Combine, which actually comes built in with the Apple iOS development environment. And if you'd like a SQLite database, very similar to Room, there's also a third-party library called Yap Database. And finally, if you'd like dependency injection, very similar to Hill, there's a library called Resolver. Let's move on to app lifecycles and architecture patterns. So when the app has been terminated or it hasn't been run yet, it's in a not running state. When the app comes into foreground, it goes from an inactive state where it's loading up but cannot yet receive user events to an active state where it can receive these user events. Then, if the app is about to go into background, it shifts back to inactive, then to a background state where it can still execute some code. From there, should the app come back into foreground, then it can shift back to inactive, then active state. Or if the app no longer has anything to execute, the OS will automatically put it into a suspended state. From there, it can come into background, say if there's a poll timer that needs to wake up and tell the app to do something, or if the system decides it's running out of memory, it can terminate the app, and then we're back to the not running state. So how do iOS developers handle these life cycles? Well, we can use the Delegate, which is basically the singleton application callbacks for the life cycles, or a scene delegate, which is callbacks for Windows. So think iPads with multiple windows. You can have, it can handle the UI life cycles for that. If you're working with Swift UI, the app delegate can still be configured to be used from your app, and the scene delegates have been replaced by scenes. So let's focus on the app delegate since it's our application level lifecycle and see its callbacks. So for example, if we are not running and we finished launching, we're coming back into the foreground, we have the application did finish launching callback. Say we're going into our inactive state, we're entering the foreground. We have the will enter foreground callback. Then when we're about to, or we have become active, we're ready to receive user events, we have the did come active callback. Then say we're going back in the background, we're shifting back to inactive state. We have the will resign active callback. You get the gist. Okay, let's take a look at some common architecture patterns in iOS. So a lot of common architecture patterns in iOS mirror what we have in Android. So there's MVC or model view controller. This is also known as massive view controller, unfortunately, because it generally turns into this giant guide class that's not really great for modularization. Now, this was the way that originally, back in Objective-C time, that iOS was meant to be developed and architected with. There's actually a built-in UI view controller that was meant to control all of your views and interact with models. However, things have changed, architectures have moved on. Now we have MVP or model view presenter, with the presenter basically replacing our view controller with a presenter class that we're just creating ourselves. Unfortunately, this also suffers from the same massive presenter problem we have at Android. And we have an Android favorite, which is MVVM. We're going to go more into this in a moment. And finally, for those ambitious modularizers, there's Viper. Unfortunately, Viper is quite complex and can take a presentation all by itself. So today we're going to just focus on the MVVM. Now, it's important to note for Android developers getting started in iOS that if you're using MVVM in iOS, there is no view model class or type built in with iOS that controls one lifecycle for you. There's just, if iOS developers are using view models, that's just a regular class they've just created for themselves. Usually it will have properties or functions for the view to react off of or update. And it's really up to developers to determine how much business logic they'd like to put in the view model or a model or repository, some other structure. Okay, any questions so far?
I was looking for the Android Android app lifecycle diagram. Did you show that?
No, I only showed the iOS lifecycle diagram.
Okay. I was thinking, I'm like, yeah, that'll be like a big plate of spaghetti because it's like, well, there's like 600 different versions, and you can kind of get to all the different states from each other, and it's kind of a mess. So I was excited to see how it compared, but understood.
Yeah, the iOS lifecycle is a lot simpler. They also do have this UI window lifecycle, which is different, but they have their own callback structure. But in general, like I feel like the kind of general idea is it's sort of like the Android lifecycle, but in some ways a lot simpler.
That's been my perspective as well.
Are there any other questions? Okay. Final topic, everyone's favorite topic, which is Swift UI versus Jetpack Compose. So if you're building in Swift UI, you need to declare a struct of type view, and this view is actually a Swift UI type and requires you to have a var body of some view, which will have some content. This is very similar to in Jetpack Compose, where you declare composable that will have some content. Now, this particular Swift UI view is making a pet details view in my pet sample app. And you'll notice that it has some declared state variables like name and update favorite status, which is a lambda. This is very similar to in Jetpack Compose, where we can pass in some parameters of state variables or declare new state variables that we need to use. This is how we're able to get content to fill in our Swift UI view. Now in Swift UI, we use vstack for columns and hstack for rows. So here we have an image view in my vstack or column on top of my hstack, which has a row of text. This is how we're able to get this image of a cat above this row of text that describes the cat. Now, what about customizing our views? Well, in Jetpack Compose, we use modifiers to do this usually, but in Swift UI, we're always going to use builder functions on the Swift UI view. So for example, here we have two images side by side of Swift UI versus Jetpack Compose. And you'll notice that in Swift UI, we can use these builder functions in order to adjust the features and customize our Swift UI views, just like how we would do so with a modifier in Jetpack Compose. Now that we have a general idea on how to create the UI, how do we get the data from, say, our view model into our UI? Well, in Swift UI, you can either pass the view model into the constructor, or you can use the builder function called environment object to pass, for example, our state object view model. And what this does is it allows us to refer to this view model from our Swift UI view and any of its children with the @environment object. That's how we're getting this data. This is very similar to in Jetpack Compose, where we can get the Hilt view model and then pass it as parameters down into our Jetpack Compose composable. That's all for me today. I hope you learned something new about iOS development. If you have any further questions about Android or iOS, or would like to see more examples about Jetpack Compose versus Swift UI, I will be posting my GitHub repo for pets.sample app. Are there any other questions?
Doesn't sound like it, but we do have some compliments rolling in. Great presentation. Thank you from C. And I will definitely echo that and say thank you very much, Lauren. That's a great primer, great way to, like, if you've been doing Android for a while and kind of wondering like, what would I get into going to iOS? I think it's a really good kind of overview. It lets you know some of the terminology to be looking for, some of the things to be looking for as you get started in that space. So thank you very much.
Thank you.
Any other questions? Great. Well, I'll just say thanks again, Lauren, and it's always a pleasure to have you at GDG Dallas.
Thank you.